Hi, Robert. Terribly sorry I'm late. We had an energy panel that overran slightly.
Hey there, Archie. Nice to meet you.
And you. So I'm really looking forward to this talk because I've seen one of your recorded talks already, and it was absolutely fantastic. So I think we're going to learn a lot. And we're both neuroscientists by training, I think. So that's also exciting. Dr. Robert Meyer is here to talk about decarbonizing cement and concrete. He's the CTO of Alcemy, and he's a data scientist and neuroscience researcher by training. And he worked at the German tech unicorn Flixbus before diving into the Entrepreneur First program, where he met his co-founder Leopold, and they started Alcemy, a machine learning startup to accelerate the decarbonization of cement and concrete supply chains. And today he'll be telling us about how to use machine learning to ensure the reliability of these low carbon recipes for cement. And I've seen Robert speak on this talk before, and I know it's going to be fantastic. So the floor is yours. Thanks, Robert.
Thank you very much, Archie. That was a very kind introduction. Can you hear me?
Yep.
And is the presentation visible? And then
Yep, you're good to go.
Great. Okay. So yeah, welcome everybody to my talk for the PAW Climate 2022. And basically, I'm going to talk. Wait, now it's going to move. Yes. I'm going to talk about three different things. So the first one is the big problem that cement and concrete has as a supply chain. And then secondly, we're going to talk about how we can actually solve this problem with new cement and concrete recipes, as Archie already said that this is going to be a major part of the talk. And then we're going to do a big deep dive into why on earth you actually need data science and machine learning in order to make that happen. So what is this big problem that I'm talking about that cement and concrete has? So concrete is the most used building material on Earth. In fact, the only thing that mankind consumes more of than concrete by volume is water. And it's just getting bigger because it's expected that by 2060, the entire world's building stock will double. That means from now until then, every month, we will build the equivalent of New York City. And that's good news because on one hand, that means there's more housing for an ever-growing population. And on the other, that is more infrastructure for the developing countries. But that comes with a heavy price tag. And this price tag is that concrete has a massive carbon footprint. So if concrete was a country, it would be the third largest emitter, right after China and the US, with about 8% of worldwide emissions. So where do these emissions come from? To understand that, let's take a step back and figure out how concrete's made. It all starts in a quarry, and that's a limestone quarry to be precise. And that's great because limestone is available all around the earth, meaning it's available in these gigantic quantities that are needed in order to build our world. And then this limestone is taken out of the quarry into a cement plant where it's refined into cement. This cement then is the most important ingredient for the concrete. So it's taken to the concrete batching plant where you add sand, water, and gravel. And then you have concrete, which you then can transport in these mixing trucks directly to the construction site where you can pour it and build houses, bridges, you name it. And interestingly, if we look at this entire supply chain that I just sketched here, basically the entire carbon footprint, about 90%, is from a single step. And to be precise, a single step in the cement plant. And that is the rotating kiln. So the rotating kiln is basically the step where you take the limestone from the quarry, and beforehand it was a bit crushed, and then you heat it to 1,450 degrees. And what you get out of at the other end is something called clinker. And clinker is basically the stuff that gives cement and concrete these nice properties of actually getting hard and being able to build stuff with it. The problem is once I actually heat the limestone, what happens is that the CO2 that was bound in the limestone gets released directly into the atmosphere. And that's important. That means it's inherent to the production process. And that also means we cannot mitigate these CO2 emissions with renewable energies, for example. So if renewable energy isn't an answer for cement, what is then? So if there's this huge CO2 footprint, how can we not entirely get rid of this, but slash this by a huge amount? So here's the solution, or the one that we in our company like to propagate because it's rather straightforward. So let's again look at what concrete is made out of. So basically what you see here is the general setup of regular concrete. So basically we have a bit of water, we have a bit of plasticizer or some chemical admixtures, we have sand, gravel, and then the most important ingredient, cement, which gives these nice strength properties. If we take a closer look into what cement is made out of, basically speaking, cement is made out of just two things. So one is the clinker. So that's the stuff that's coming out of the kiln. That's the stuff that has basically, or is responsible for the entire CO2 footprint. And then there are so-called supplementary cementitious materials. And these are, basically speaking, just filler materials. Some of them have their own carbon footprint, like fly ash or slag, which are byproducts from coal power plants or steel manufacturing, but others are actually carbon-free. So we are mostly interested in something which is called limestone flour, or just fine limestone, which is basically limestone that has been ground very, very finely without burning it, meaning there was no CO2 released, and therefore it doesn't have a CO2 footprint. So now the idea is actually very, very straightforward. Just replace the clinker with CO2-free filler material. So that's basically what we want to do. Just reduce the clinker in this entire mixture. So if this is regular concrete with regular cement, with lots of clinker and a high CO2 footprint, just simply by doing this, replacing the clinker with, for instance, limestone flour and a bit more admixtures and plasticizers, we can actually reduce the carbon footprint by 60%. So then we have here low carbon concrete made out of low carbon cement, simply by replacing the clinker with CO2-free filler material. And as I said, that's a very, very powerful lever in order to reduce the carbon footprint, because we can actually slash it by around about 60%. And that is not a pipe dream, because we've actually done it. So we created these new concrete recipes. We tested them in laboratories to really make sure they're feasible building materials. And we even moved them onto real construction sites. So for instance, what you can see here is a construction site from last summer where we poured the foundation of a garage. And this summer, we moved a bit on, so there will be 3 stories of the next Berlin skyscraper will also be made out of this low carbon concrete. So this exists, this works, this is great. So you might ask yourself, okay, so low carbon concrete is there, hooray, but why on earth would you need a machine learning company or a data science company in order to produce that? There was nothing data science related yet. Okay, so in order to understand this, you have to bear with me a little bit. It's going to be a bit of a lengthy explanation, but I hope you can bear with me for a while. So as I said, the most important property of concrete that basically makes it this super duper building material for the world is its compressive strength. It's its property to withstand huge amounts of pressure. We can actually measure this compressive strength of concrete in megapascal that you can see here. And usually what you need for most building, like 80% of applications, it's something around 25 or 30 to 50 megapascals right here. So this is the order of concrete we're usually looking at in mass applications. So if I say, concrete's most important property is strength, how can I actually modify the strength of concrete? There's basically 2 levels. So one is the most straightforward one. It's basically using better cement. So if I use stronger cement, I get stronger concrete, which is depicted here by these 3 different colored lines. So the green line depicts like weak cement, the blue one is like medium strong cement, and the red one is strong cement. And if I go into that direction, I can see if I take stronger cement, I get, as you can see on this axis, on the y-axis here, I get out stronger concrete, straightforward. But there's another level that most people don't know of, but which is even more powerful than just using better cement, and that is using less water. So for example, that is what you see on the x-axis here is the water-cement ratio. That means, for example, here, for a water-cement ratio of 0.7, that means I take 7 liters of water per 10 kilograms of cement. And if I then take this rather weak cement, I get round about 28 megapascal for my resulting concrete. But if I now go and actually cut the water in half, so I don't take 7 liters, but just 3.5 liters, but I leave everything the same, what will happen is I get much, much, much stronger concrete. So just by cutting the water in half, I actually end up, even with this weak cement, with something like 60 megapascals. So that is a very, very fine lever in order to really increase the strength of my final building material. It's just reducing the amount of water. But that is not an easy thing to do because it comes with a hook. So basically, if I'm operating here in this high water regime around like 0.6, 0.7 water cement ratio, basically my building material, concrete, is very, very, very robust to errors. So for example, if my cement is actually fluctuating in strength, meaning I assumed it was 50 megapascals, but for example, it's 55 base strength, then even if that happens, that's not problematic if I'm operating in this high water regime, low strength down here. And even if I, for instance, get my dosage of water wrong, so if I'm here and I add a little too much, then basically my consequence in the resulting strength of the concrete is rather low. So basically down here, my concrete is very forgiving. If I make any mistakes in my cement or any mistakes in my water, that's fine. Everything's going to be fine. But if I'm operating up here in this low water, high strength regime, what you can see is that the curves are farther apart and also the slope is very steep. Any error I make will have severe consequences. If I get my water dosage wrong, that has severe consequences on the resulting strength. If the cement strength is not reliable, this will also have severe consequences on the final strength of my concrete. So everything up here is really, really difficult to produce. And you can see this if you actually order that kind of concrete in a concrete batching plant. So if you order regular concrete with like 0.6 water cement ratio, you phone up your trusted concrete plant, then the mixing operator alone will be able to ship your order. So you order this regular concrete, they will batch it for you, ship it to you, and that's it. One person is enough in order to get that handled. But if you now phone up the concrete plant and you actually order something much more difficult to make, let's say you want some high strength concrete with a water cement ratio of 0.35, then actually people will start to get nervous in the plant, and the mixing operator alone will not be able to do this alone, and he will be accompanied by 1 or 2 lab personnel. And they will actually make loads and loads of tests at the plant and look over the shoulder of the mixing operator to really make sure that the concrete has the right consistency and the right amount of water in it, and will really, really, really take care that everything goes well. And even one of them will actually join the concrete on its way to the construction site and remain at the construction site and do further testing to really, really make sure everything's fine and there are no severe consequences. Okay, so you might be wondering right now, okay, fine, okay, I can change the strength of my concrete either by cement or by less water. What has that to do with low carbon cement and low carbon concrete? Well, the hard truth here is that low carbon cement is basically because we replaced the clinker, which is this nice material that gives the strength, with filler material, so to speak. We actually have a very, very weak cement in our hands, meaning if I use low carbon cement and I want to get something out like concrete strength out that are useful in everyday mass applications, so something between like 30 and 50 megapascals, I already have to operate in a very, very low water regime with like 0.35 or 0.4 water cement ratio. And this means, unfortunately, this is also very, very tricky to produce. And there will then usually be 3 people involved. And actually having 3 people involved is kind of bad for concrete because that makes it expensive. I mean, if you order the everyday concrete here, that will cost you around 8 euros per cubic meter. But if you order high strength concrete here or low carbon concrete with regular strength, because of this huge overhead in human power that is needed in order to produce that and the severe error consequences, although the ingredients are the same or even cheaper, in the case of low carbon cement is actually cheaper because clinker is the most expensive ingredient, the resulting concrete price will be much, much higher, about 200, 300 or even 400 euros per cubic meter. And that's bad because concrete is such a successful and widely applied building material simply because it's so cheap to build with. So in order for low carbon cement and low carbon concrete to become a mass application, it has to economically be able to compete with regular concrete. And that's basically what our company does. So we use digitization, automation, and machine learning and control in order to make this handle so that one person can actually handle this instead of 3. And actually the lab staff can then focus on much more important work and scale themselves to more construction size. So with that, then low carbon cement and low carbon concrete can economically compete with regular concrete, and then they will actually take over the mass market. And then there's an incentive to actually use this. Okay, so how do we do that? So first of all, I said there's basically 2 things we need to get right. First is one in cement. We need to have a reliable compressive strength already in the cement. And the second thing we need to get right is on the concrete side of things, we need to have reliable and traceable water dosages. Basically, this is referring to these 2 directions of errors that I can make in my concrete recipes with low water, right? So I need to make sure that the water is right, so removing that kind of error, and I need to make sure that the cement is actually reliable. So if I order something that should have 50 megapascals, that I can actually be confident that it will have 50 megapascals of compressive strength. Okay, let's first focus on how to do that in cement, how to get reliable compressive strength. So, as I said, this is important because we want to reduce clinker, which means we get a less robust concrete. So basically, if the strength of my cement already fluctuates, so the base strength of my cement, because we have to operate in this low water regime, what will happen to my final concrete is it will fluctuate tremendously. So if this is the strength at the time of production, basically my low carbon concrete recipes with very few drops of water will actually amplify any problem that is already present in the cement strength. So what I want, instead of this fluctuating curve, I want to have a very consistent homogeneous product. So this should actually be a straight line. The problem is actually getting cement strength right is a very difficult endeavor. And the reason is because measuring strength, be it cement or concrete, actually always requires you to make a concrete cube. So if I want to measure the cement strength, I take a standardized amount of sand and a standardized amount of water, form a little cube, let it sit and harden for 28 days, and then you have to crush it. So it kind of looks like this. So basically you have this this cube that was hardened for 28 days, and then you crush it, and basically then you can measure your strength. But that's quite problematic, because that means for everything I produce, the core quality of my product is only known to me a month after I produced it. And then already all of the cement I produced and all of the concrete that was made out of it will already have been shipped and used at construction site. So basically I can only correct my errors a month after I produce stuff. And this is, of course, very, very difficult to handle. And if I can only react with a 28-day delay, getting something like very homogeneous and reliable is really, really difficult. So what we now do is basically trying to predict the 28-day strength at the time of production. So we get really rid of this 28-day delay. A quick side note, you might be wondering, okay, so yeah, cement strength fluctuates. Why does it fluctuate? As I said, cement is made out of a natural ingredient. It's basically limestone that has been ground very finely, has been burned and ground. So basically the properties of the chemical and mineralogical properties of the limestone propagate into the cement and have then like strong influences on my compressive strength. Because if you look into a limestone quarry, every cubic meter to cubic meter looks very, very different. I mean, you can see it by the colorful stones that you have in a limestone quarry, that there's like lots of variation in nature. So this is what you can see here. So maybe on a Tuesday, last Tuesday, I got very, very fine limestone, which actually produced then cement that got very, very strong. But a week later, I'm unlucky and my limestone is not that well from this chemical and mineralogical composition, and I get some cement that doesn't get that strong. So this is how these fluctuations in the cement strength actually happen over time of production. So the idea now is that we counterbalance these fluctuations with another property that has a strong influence on the finer strength of the material, and that is the fineness. Because the more fine I actually grind my cement, the more surface area it has to interact with the water and to actually get stronger. So basically the idea is then if I have some limestone that yields very, very high or high strength cement, I can actually counterbalance this with grinding much more coarsely and vice versa. So if I have something that doesn't get very strong, then I grind more finely, and basically then the resulting material, due to these counterbalancing, will be something that is very reliable and has a homogeneous strength over like weeks or a month of production. So if I want to produce a cement with 50 megapascals, I can really make sure that year round I will produce a cement that will have 50 megapascals of compressive strength. So here's how that works in the final step of the cement plant. That is the actual grinding of the cement. So what you can see here is like the raw ingredients, like clinker and slag. So it's like clinker, that's the main ingredient, and then here are the supplementary cementitious materials like fine limestone. All of them get chucked together. They get ground then together in the cement mill. And then there's this separator or filter step where you can separate fine from coarse particles, and stuff that's still too coarse have to take more tours through the cement mill. But it doesn't end here. So basically, right after the separator, before the cement enters the silo, they take regular samples. And these samples are automatically analyzed with X-ray diffraction, X-ray fluorescence, and a particle size analyzer. And this gives us really the full picture of the material, because that's the mineralogy, that's the chemical composition, and it's the actual distribution of particle sizes. And this full picture of the material is then exported into our cloud system, where we then run a machine learning algorithm to take this full picture of the material in order to predict its strength it would develop if I would form a cube out of it, let it sit for 28 days and crush it. So really predict the 28-day strength of the material. And now we can immediately react and don't have to wait a month until the actual strength result is realizing. So basically, if the prediction says, hey, you're producing something that's getting too strong, then we can counteract and say, hey, grind more coarsely. So we can actually calculate optimal finest set points for the cement mill, feed that back into the plant, and the cement mill will be changed to grind a bit more coarsely. And then a few hours, like 1, 2, or 3 hours later, the next sample is taken, and then everything will be on target. And then this loop runs 24/7 year round in a cement plant in order to get cement strength really on target. And here's an example how that really then turns out with real data. So what you see here is data over 5 years. So each of these blue lines correspond to a different strength. So down here is the 2-day strength, here's the 7-day strength. But what really matters is the final strength that's developed after 28 days. So this is what you see up here. So each and every blue dot really corresponds to one of the cubes that you just saw in the video that was hardened for 28 days and then crushed. And as you can see, here's the production volume over 5 years. And you can see there's quite some variation, right? It goes like from 50 to 65, 66 megapascals over time. And then basically from then on here in 2019, we started with our control loop actually live in this particular cement plant. And we were able to reduce these fluctuations by around 25 to 30%. And this is actually quite a lot for an average cement plant. So usually that amounts to savings on the order of 300,000 to €500,000, like a mixture of different things. So it could be savings on grinding energy. It could be savings on actual CO2 certificates, because now I can actually really reduce the clinker even within the cement standard that I currently have, and just counteract with more fine grinding. Or because I have a better quality cement, I usually can also charge a bit more with my customers. So yeah, so basically this is the first application of the machine learning in order to get the cement strength right. I was also asked to be a bit more technical. So maybe here are some learnings that we drew on the way. Maybe for the ones that are interested, like this is how the data actually looks like. It's basically for every plant that we have a giant spreadsheet. So here is the feature vector. So here are some numbers that are related to the actual fineness and the particle size distribution. Here are some numbers that are related to chemical compositions. And on the right here, you can see some numbers that are related to the mineralogical composition of the actual material. So basically this one of these rows makes up a feature vector, and on the left here you can see the actual results of the 28-day strength experiment where they crushed a cube, and basically this is then our target variable, and with this giant spreadsheet we can train our machine learning models. In fact, it's the actual feature vector is a bit longer. This is like a subset of all the measurements that are taken from the XRF and XRD and the PSD, but basically this is how it looks like. And I mean, we are a machine learning company, so we like to play around with machine learning algorithms, and we tried a lot of them. Of course, we tried PyTorch neural networks because who doesn't want to call themselves a deep learning company? And PyTorch is really great to play and tinker with. So of course we tried this, but we also tried support vector machines, Gaussian processes, XGBoost, you name it, like loads of different stuff we tried. But unfortunately, and this is usually, I mean, and this can be a reality for you as a machine learning company, actually the model that you're using doesn't make huge of a difference. Because all of these basically show none to marginal improvements, but even worse, all of them are very, very black boxy. And what we actually ended up with, which is deployed in production, is a combination of just regularized linear regression, and on top of that, a random forest that corrects the error of the linear regression. And this is great because if you have machine learning in production, simple models are your friend. Because I mean, we are using our machine learning in a control loop, meaning we really need to be confident that the machine learning learns some causal relations and not just some spurious correlations in the data. So just by looking at the coefficients of the linear model, we can already identify if the model picked up some meaningful relations in the data. Because if the coefficients show stuff that is known to cement process engineers, then it's great because then we can use that in steering. For example, we regulate or steer the cement by modifying the fineness. So also the coefficients should pop that out, right? So there should be a strong relationship between the fineness of the material and the final resulting strength, and how the model makes the prediction. Or stuff like titanium dioxide reduces strength, or C3S fosters strength, and stuff like that. So if that pops out in the linear coefficients, we're happy because that basically tells us that the model picked up something meaningful. So real machine learning in production, simple models are your friend. What we learned, what is actually way more important than the models themselves, is the pre-processing of the data. So for example, what is really important with any physical data, like from physical processes, like we have this XRD and XRF values, is you need to do outlier filtering, because I mean, these experiments tend to yield sometimes spurious or erroneous measurements, and they need to be discarded. But the problem is sometimes outliers actually tell you something because something happened in the actual cement plant, which was bad. So our model could actually learn from this. And really figuring out when something basically tells you something and when something is so weird that it's supposed to be an outlier, finding this threshold when to discard stuff and when it's still feasible for learning, that's usually a good place for a hyperparameter optimization. Also, what we learned, which is very important in our setting, is proper imputation, because oftentimes the measurements of these experiments of these devices tend to fail and miss. So we do need to do proper imputations, and proper imputation also encompasses, meaning if you have samples that basically have no features because all of them or the majority of them is missing, discard them. There's no need to learn from these kind of data, because that will introduce strong biases in your model. But if you have just a few missing values, it actually might be worthwhile to apply machine learning already in your pre-processing step and trying to predict the missing feature from all of the other features that are there. But if you have columns that have many missing features, then using machine learning in order to impute this will again introduce heavy biases into your model. And so deciding on which of the three to do when, that is also a good place for a hyperparameter optimization. Okay, so that was a quick detour over the learnings that we had. So coming back to the overall topic, so I said in order to make low carbon concrete scale and work, what we need to do or solve is basically two problems. So the first one is in cement, getting reliable compressive strength. And I just showed you how we do this with machine learning. And then the next one is actually in concrete, because both need to be in place to make low carbon cement and concrete scale at the mass level and for mass application. We need to have reliable and traceable water dosages. So for now in cement, we talked about this error into this up direction, and now we're looking into the error of actually making wrong water dosages. And you might ask yourself, why is it so difficult to actually get proper amounts of water into my concrete? Well, because there are different sources of water, how water can actually enter the concrete. One is fresh water. That's fine, because that's the actual water that you can dose, that you can weigh in a scale. So if you want to dose 100 kilograms or 100 liters of fresh water, just measure it and dose it. That's fine. But there's also something called recycling water. So whenever a concrete truck returns to the plant, they have to clean the drum for the next batch of concrete. And this water that was used for cleaning the drum cannot be just put into the sewer, but it has to be recycled. So basically, it goes into a recycling tank and has to be over the course of the next batches and next concrete deliveries used in order to or dispensed into the coming concrete and future orders. So basically, if I have to mix my concrete with fresh water and recycling water, because there are already concrete particles in there, it has a different density and can already have like solid mass in there. So if I dose 100 kilograms of recycling water, I might end up with just 90 kilograms of water and just 10 kilograms of solid mass. And actually figuring that out, how much is much, is really, really difficult. Recycling water can actually have severe consequences on the actual amount of water that is available to the concrete in order to form a reaction and get hard. Another source of water is the moisture in my sand and gravel. I mean, cement itself is stored in a silo, and that doesn't get wet, and it shouldn't, because then it would get hard. But the sand and the gravel usually is stored in plain sight, so when it rains, the stuff gets wet. And when I then start dosing that into my concrete, then of course, if I dose 100 kilograms of sand, there might even be 5, 6, 7 kilograms of it just already water. This is then another source of water in my concrete. And measuring actual moisture of sand and gravel, there are moisture sensors, but they are quite unreliable, and you actually have to calibrate them well. And in the everyday life of a concrete plant, where stuff has to go boom, 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 super, super fast, usually nobody has the time to really take care that the sensors are properly calibrated or really cares about the sensors at all. And unfortunately, so basically sand moisture is really hard to measure also, and especially moisture of the more coarser aggregates like gravel. And then there's unfortunately another source of water which shouldn't happen, and that is the water that is added at the construction site. So usually that's frowned upon, and you shouldn't add water at the construction site, only plasticizers, but people keep doing that. And if you had, for example, a batch of low carbon concrete in your drum, and you would add water to that at the construction site without properly really taking care how much water there is, the concrete is going to get flawed. That's kind of bad, but it happens, unfortunately. So basically what we're building, and this is going to be released in about 2 to 3 weeks, is an application to make this water, make every drop of water traceable. So basically what we're currently building is a cloud application that takes the data from the plant, especially the power consumption of the mixing drum, because that's a very, very good correlate of the actual water content on consistency of the concrete. And more important, we also equip concrete trucks with sensors to really, really monitor the concrete when it's driven from the concrete plant to the construction site. And basically, what we have there in a concrete truck are basically 3 different sensors. So one is an oil pressure sensor here, which measures the oil pressure that is needed in order to rotate the drum. And that's another great correlate of the consistency and the water content of the concrete. Because I mean, if it's very stiff, then it's very hard to turn the drum. If it's very fluid, then it's easier to turn the drum, and we can see this in the oil pressure sensor. Then of course we have a drum speed and direction sensor, because I mean, drum rotation in one direction means it's mixing, and in the other direction means discharge, so that the concrete is actually poured on the construction site, and then basically it's easier to identify where we currently are in the process of like, are we still transporting, etc. And this is a bit of unfortunate, but this is by far the most powerful sensor that we equip, and it's the most easiest and straightforward one, is just a flow meter. Here's the water tank where you can add water directly into the drum, or water that you can use for actually cleaning your truck. We just add a flow meter here to really be able to track every liter of water that is taken out of the drum. And basically in combination with, for instance, the drum speed and the direction sensor, we can basically reconstruct whether the water was dosed like for cleaning, or whether water was really, really dosed into the truck drum. And then all this data is fed into our application, and there basically what we're building is an app that can be used by lab staff to multiply themselves. So now every drop of water is accounted for, and we make this visible to the lab staff. So basically they can now see every panel here. What you can see corresponds to one particular construction site, and they can supervise and monitor each and every construction site from the laboratory, and they don't have to ride together with the concrete anymore to the construction site. So they really see how their concrete behaves right when it's dosed and mixed at the plant up until it's really discharged at the construction site. And it makes it like super, super powerful. And then, yeah. So basically with these two applications, the machine learning control loop in cement and this application that makes every drop of water traceable, we gonna unlock or reduce this massive green premium on low carbon cement and concrete so that low carbon concrete can actually now compete with regular concrete and will in the medium or even in the short term already overtake this in 80% of the applications. Yeah, so basically this is a product that has been live now for a bit more than 1 year and a half and now 5 or 6 plants already. And the concrete application is still under construction, but we're going to release it in 2 to 3 weeks. Yeah. And then in this combination, we will actually then showcase that both work together by supplying low carbon concrete to the Edge East Side Tower in Berlin, building an actual skyscraper with that. So yeah. Thank you very much. Here's a quick recap. So basically, concrete is responsible for 8% of worldwide emissions. That's kind of bad. But low carbon concrete exists. That's a good thing. The only problem is it has a very, very high green premium because there's so much manual oversight and labor involved. And the reason is because you need reliable cement strength and precise water dosages. But we can use machine learning to get cement strength on point, and we can use basically a data application and harnessing all the data and new sensors on trucks in order to make water dosages traceable. And with this combination, then we can actually really reduce the green premium on low carbon concrete. Thank you very much. Are there any questions? Oh, here's one. Why not grind really fine all the time? What are the cost energy consequences? Yeah, well, so the problem is, I mean, you could, this is a valid strategy is to grind pretty fine and then try to reduce the amount of clinker that you already have given in a particular cement standard. The problem is that the energy consumption and the energy amount you need to grind more fine grows roundabout exponentially with the fineness you want to achieve. Yep. Are there any more questions? Then I'd say thanks for your attention, and yeah, let's. I'm very excited to decarbonizing this industry because they have a very massive footprint with 8%. Actually, I think you're on mute.
Thanks. Sorry, I'm now here on two different computers because my other one froze just as I joined to ask you some questions.
Fair enough. I think we have like 2 or 3 minutes left. If you have another question, then
Yeah, I do. So, firstly, I think it's fantastic, inspiring how you started with a clearly defined ML problem, and then you realized there was this other problem that wasn't really to do with ML at all, but you had to go crack it in order to make this product viable. I think that's awesome. On the ML side, it seems like a case where there's a very asymmetric loss function, in the sense that if you overpredict the strength of the cement, you get in much more trouble than if you underpredict the strength of cement. Is that right?
Roundabout, yeah, but it's not that severe actually, because it's even yeah, you're right. If stuff gets too strong, that is not that bad. If in comparison to if it doesn't get like too weak, but we don't have to actually account for that in our loss function. So we have a very symmetric loss function, and it still works. So we try to keep things as simple as possible. Because I mean, we can see it in the data that basically now the fluctuations are really much less than before. So,
and on the explainability of the model, you mentioned that you could often find relationships that were confirmed by domain experts. Were there any things that you spotted or the model picked up on that experts were surprised by, but then realized subsequently, oh, actually, that does make sense?
So, for example, the very strong influence of titanium dioxide was a bit surprising. So they knew that was the case, but then they actually also did some more experiments with that, with different mixtures, and figured, oh yeah, it's even bigger than what we anticipated before. So that was a pretty cool finding.
So you're kind of doing a bit of material discovery on the way by accident.
A bit, yeah.
Awesome. I think that brings up to time. Sorry for my technical issues. My other screen seems to have disappeared now.
No worries.
Thanks again for a really informative talk.
Thank you for having me, and enjoy the rest of the series.
Thanks, and you. Bye.
Bye.